All right. So we look at the mean value theorem, and first of all, we want to look at what the mean value theorem is from the definition point of view. Then we'll also go through an example to give us a broad understanding of like we try to make sense out of the definition using an example in simple terms. Okay. So similarly to Ross theorem, for mean value theorem, first of all, before you test whether the function that you're given satisfies the mean value theorem on a given interval, you have to ensure that that same function that you're given, let's just say that function f should be continuous on the closed interval, which is a comma b. Okay, it should be continuous at that point, meaning there should not be any um, instant changes in terms of direction of a function in terms of the sketch, such that let's say you have something like this, then you have that sharp change there. We would not say that is continuous. And let's say you have a graph or a sketch that is in this manner, maybe it ends at that point, then starts from this point going, we don't know, this is not continuous because of the gap that we have here. And this is usually the case when you're talking about piecewise functions. Okay, so to really know what a continuous function is that, let's say you have something like this. If you have something like this, that's continuous. You have something like this is continuous. You have that is continuous. Okay, so we should make sure to say the function that we're given is continuous on an interval, on the given closed interval, which is a comma what, a comma b. Okay, so for a is the lowest value. So for example, if you're given 0 comma 1, okay, so meaning the value of a is 0 and the value of b is what, is a 1. That's what we talk about right there. Okay, so we should make sure to say it is continuous on that particular interval. All right, so the second thing that you have to ensure is that your function f should be differentiable on the open interval a comma b. So what do we really mean by this? Let's say you are given something like that. We are given something like this just to give us an understanding of what we are really talking about here. Let's say this is our a and this is our b. Let's say those are our intervals. So we should ensure to say our function should be differentiable between a and what, a and b. So between these 2 points here, our function should be what, should be differentiable, but not differentiable at a or at b. Okay, so that means if you have your closed intervals that is 0 comma 1, so meaning your function should not be differentiable at 0 or differentiable at 1, but between 0 and 1. Anything between 0 and 1, that's where your function should be differentiable on. Okay, so having said that, if this is satisfied and this is satisfied, or we find out that is true, then there is a value c, or some values, at least one value for c. It depends on the nature of the function that you are given. Sometimes you have two values of c, sometimes it can be one, it can be, yeah, multiple values of c. We can just say, okay, there is at least one value of c that is in between, but I'll use member of the open interval a comma b. So meaning it's not a or b, but it's just in between. um, it's just in between a and b. And again, for example, if you have, let's say this is your a and this is your b here, anything that is this side is not counted, and anything that is this side is not what, is not we're just interested in what is in between here. So we should really take care of, or be careful with the fact that we are dealing with intervals here. It's not just any it's not just any number that we can pick. That's why even as much as a function can be continuous, when you look at the interval, maybe the interval is not maybe the interval that you are given is not really um, it's not really coinciding with the function that you are given. Hence uh, you'll be able to make some disqualification there, because if just any of these steps, like the first one, the second one, the third one is not satisfied, or let me just say the first one is not satisfied, then uh, we can't go ahead to look for where the function satisfies mean value theorem. Okay, so having said to say there is at least one value for C that is a member of, or it is in between A and B, the open interval A comma B, such that it is such that the derivative of the function, okay, the derivative of the function, then we have C here, that will be equals to, it will be equals to the function itself, f of b minus f of a over b minus what, minus a. So here I'm not differentiating with respect to C. No, what I mean is that you will be given a certain function, you have to differentiate, and you're looking for what C is in this case, and we're going to get it as x. So that function, that value of C that you're going to get should be in between what, a comma b. If you find that this the first condition is satisfied, the second one satisfies as well, but if you find that your C that you find is not in between a comma b, we should not to say the function that we have been given does not satisfy the mean value theorem. Okay, so another thing that we have to understand is that there are two important rates of change that we have to be familiar with when you're talking about mean value theorem, and even other theorems as well. Is there's what is called the average rate of change. I'll just say change there. Then the average rate of change here. In terms of this describes this describes the it describes this part, the f of b minus f of a over b minus a. Okay, so this part here, it represents the average rate of change. Okay, and this is just more like you're talking about y2 minus y1 over x2 minus x1, and we get to understand this better when we know that the average rate of change is simply just it just talks about the gradient of the what, the gradient of the secant line. I'll just say m sec. Okay, the gradient of the secant line, let me just say secant, yeah, the gradient of the secant line. All right, then we should also be familiar with the instantaneous, okay, instantaneous um, rate of change. Rate of change. Okay, so this the instantaneous rate of change from this formula that we have here is simply our f prime of C. Okay, and this simply describes the gradient of the what, of the tangent line, the gradient of the tangent line. So we should make sure to say, or we should understand that the in this case, okay, in looking at what we have here, the gradient of the secant line is equal to the gradient of the tangent line. What are we able to understand from here is the fact that the secant line and the tangent line are going to be what, are going to be parallel to each other. Okay, it's more like you have let's say you have, let this give us a picture. If you have a graph that is in this manner, let's say you have something like that, then you're going to have, let's say you have a tangent line at this point. You have a tangent line at that point, then a secant line casts the graph at 2 points. The tangent line is one that casts the graph at 1 point. So these two, they are going to be what, they are going to be parallel. So this one is one that described by what, f prime of C. Then this one is what, is the f of b minus f of a divided by b minus a. Okay, so now let's look at an example. We see we try to make sense of what we have managed to understand from this. Okay, so now let's say we're given a function f of x equals to x squared plus 2x minus 1. Then we're given that the value of a is equals to 0 and the value of b is equals to 1. And they don't usually give like this, or they don't always give like this. Let's say it's an assessment. It can be in terms of, let me say, 0 comma what, 0 comma 1. Okay, 0 comma 1. All you have to know is that this is your value of a and this is your value of b. So the first thing first, we have to ensure that this function is continuous. And according to my observation here, it's easy for me. This is just like this function is simply continuous because I have no limitations. So one of the times on which we have to be considerate when you are when you are trying to find out whether the function is continuous or not, try to see if whether it's a piecewise function or not, and try to observe if it's a rational function or not, because rational functions have limitations. Okay, they have limitations. They have their domain. The domain of a rational function is limited in some way. It depends on the denominator. Okay, so in this case, looking at this function, we know that it's continuous. And if we would maybe try to make a sketch out of this so that at least we have a clear picture of what we are talking about. um, so according to the sketch that I've come up with, this is simply a parabola opening upwards. Okay, you're going to have your vertex at that point, which is negative 1 comma negative 2. Okay, then you're going to have your point here. Okay, your x-intercept there, then another x-intercept there, and that would be something like that. Okay, it's not really perfect, but at least it gives us a picture of how it appears. Yes, we know it's a parabola opening upwards, meaning the value of p was positive. Okay, so now okay, if you'd want to come up with this, you can still just say, okay, I have my x, I have my y. For example, I said my vertex is at the point negative 1 comma negative 2. How did I come up with that? If you come to this function, if you say negative 1 squared plus um, 2 multiplied by negative 1 minus 1, this will be 1 plus, not plus but minus, minus 2 minus 1. That would be, that will give us minus 2. Okay, which is what we have there as our vertex. So you can still just come up with values to give you a picture of how the sketch is going to appear. Okay, so we know that this function is continuous. The second thing that we have to ensure is that the function is differentiable. Maybe let's try to differentiate with c. So our f prime of x will be equals to 2x plus 2. This is a constant. It becomes a 0. Okay, so we know now that the function is differentiable. Okay, so now what follows? That means there is at least one value of c, but in this case I believe there's just one value of c, because um, sometimes you're able to tell from the highest power of x that you have there. If I had x to the power 3, I could have known to say I have two values of c, because when I differentiate here, I'm going to remain with what? X squared. Okay, and in this case I only have x to the power 1, of which I'm only going to have one value of x. Alright, so in this case we are told that f prime of c will be equals to um, f of b minus f of a divided by b minus a. We are now very familiar with that. So in this case you are going to equate this derivative that you have found, the 2x plus 2, to what? F prime of b minus f prime of not really f prime, but f of b minus f of a, sorry, yeah, like that, then divide by b minus a. So in this case what we mean is that for us to get our f of b, in this case our b is 1. Okay, our b is 1 is equals to, we're going to say 1 squared plus 2, we can say plus 2, we have 1 minus 1 minus 1, that will give us a 2. Okay, that will give us a 2, and this is positive, that's negative, it's a 0, so remain with these 2 here, so we have a 2 right there. So now what about f prime of 0? F prime of 0 will be 0 squared plus 2 multiplied by 0 minus 1. Okay, So meaning we remain with negative 1, but we can't just say minus 1 here. Remember to say this is supposed to subtract, so we're supposed to say minus 1 divide by uh, b minus a. Okay, so in this case you're going to say our b is 1 minus our a, which is 0. So what are we going to get? You're going to get 3 over what? 3 over 1, which is just a 3. So we're going to say 2x plus 2 will be equals to 3. So what do? We say 2x will be equals to 3 minus 2. So 2x will be equals to positive 1, meaning our x will be equals to 1.5. I mean, not 1.5, but 0.5, which is 1 over 2. Yeah, that's our value of x. And what you're about to observe is that if you have the interval a comma, I mean a comma b, which is 0 comma 1, the 1.5, why do I keep on saying 1.5, but the 0.5 rather, or the 1 over 2 is in between what we have here. Okay, and hence it satisfies mean value theorem, and that's the conclusion that we were looking for, and that's how you go about mean value theorem answering such a question.